All right, so being absent-minded as I am, I forgot to mention something very important last time, which is, first, class attendance is not mandatory. But second, if I do remember you from class, especially if you ask interesting questions and so on, I will give you some bonus points when the final project comes, right? So that's my reward for class participation. Okay, it's a slightly informal, but I do remember people, especially the faces. Names is very hard for me, but we'll see. All right. Okay, so let me give you some idea of what I want to do today, right? And I mean, all of these things are going to be important for the rest of the class. So I do want first to start with an introduction to Scala. And I will really try to do two things. One is give a broad introduction to Scala as a language. I have no intention of going through all the features, all the things. I just want to get you excited about Scala. Why should you program in Scala in the first place? And the second thing is I want to spend time on Scala actors, which is the thing I mostly care about and is the model you're most unfamiliar with. Okay? So at the end of today, I want to essentially have a decent starting point to start learning Scala as a language, but a very good starting point from the point of view of what are these actors and how can you use them. Okay? I still want, if we have time, since we have two sessions today, to wrap up the discussion about what distributed systems are all about, right? That's going to set the pace for what is it that we're going to see in this class, all right? So first, Scala. And in order to introduce Scala, I'm going to use slides from a conference where Scala was presented. Martin Odersky is one of the core Scala developers. And I mean, he has the insight of what Scala is. I have no intention to go through all the slides. You already have in the Google, on the Yahoo group that you are supposed to sign up for, right? It's on the link from the class webpage. You already have an announcement saying where the slides are, right? So let's go quickly. But I'm going to stop at the interesting points for the slides that Martin presented at the conference to introduce Scala. And gives a lot of the motivation of why bother design another language. You should always ask this question. Why do we need another language? Right? There are lots of jokes on the internet of what every language does. And maybe it would be interesting to look at some jokes about Scala. I'll try to dig up something until next time. OK. Right. So of course, lots of different languages. Some of them are extremely special purpose, like SQL. I'm not going to talk much about SQL in this class, but I do talk a lot about SQL in the database implementation class, for example, right? For example, one interesting language that I'm excited about, but for reasons that might not be obvious, is JavaScript. Why would I be excited about a language like JavaScript? Let's try to throw some reasons out. Well, so actually, as a language, JavaScript is not fantastic. Scala is much, much better. And I'm going to point out, how many people have seen some snippets of JavaScript? Right, well, you should do some view source when you look at the web page, right? And all of them have JavaScript now. So the reason I'm excited about JavaScript, really, and this can point out reasons to be excited about languages, is because it's supported very well by all the major browsers. So if you want stuff to run in the browser, you have to learn JavaScript. It has nothing to do how cool the language is or how exciting certain things are. There are interesting things in the Java language. By the way, Java language was designed in a week. All right? They're interesting in the Java language. I'll point out some of them as we go through Scala, for those of you that have seen JavaScript. But sometimes you can be excited just because of the availability of the language. That's not the case for Scala. Okay? But Scala is cool for many other reasons. Okay? Zoo of languages, many such languages. Now, to a large extent, even beyond the actors, Scala is interesting because finally the language community, right, the researchers in programming languages have done the right thing. And it's just the perfect blend of all kinds of interesting stuff. I'm going to point out what they are. Okay. So let's see what Martin has in here. Right? Right, so you have all of this discussion about languages, what's good and bad, right? Each language has a sweet spot. And an interesting question is, could you design a language that has a large sweet spot? And to some extent, that's what Scala is. All right? Now, of course, communicating between languages is really bad, but Scala does some of that well with Java. Okay? Okay. Now, actually, this puzzled me a little bit. What do these guys mean by a scalable language? I mean, this is what they mean by Scala. What they mean, and you're going to see tricks in how they do it. And maybe Scala should be taught actually in a language class, because it's a very good example of an extremely good design of a language. So it's scalable in the sense that it has enough flexibility in the syntax to allow you to invent your own subvariants of the language. And that bothered me for a while until I sit down to see exactly what that means. And I'll point it out when we reach the right slide. It turns out that if you relax a simple rule, how can you call functions? You can, in fact, get a very nice relaxation of the language that allows you to encode seemingly specific languages into a broad language. Okay? I'll point that out specifically because some languages allow one way to call functions, other languages another way to call functions. Scala allows both, and suddenly it feels much better. Okay? So so let's go through the slides. I'm sure I'll find an opportunity to show you that. Okay? Now, Scala has many things going for it. For example, it can work as a scripting language. So in fact, it can be interpreted. You're going to play with it. You're going to download Scala and fire up the Scala executable. And literally, you can type there directly Scala code. And there is a big advantage to this kind of languages because you get instant feedback on what is it that you're actually doing. And a lot of languages are like this nowadays, right? Python is like this. How many people programmed in Python? Right? I mean, Python tends to be like this, right, as an example. Right? So for example, you could do things like, oh, let's define a map. US, I'm going to go through what these things mean in a second, right? A map that maps US to Washington, France to Paris, so on and so forth, right? Then we define some sort of a function, and then you see operators in the language, like plus equal seems to be some sort of an operator. So what is this capital now? It's some sort of a map. We don't quite know what it is. It's probably some sort of a dictionary, right? Then this operator plus equal probably adds entries to the dictionary, right? So it seems that this language has dictionaries, or maybe it's not in the language, maybe it's in some sort of a library, has operators that make your life easier, right? Then we can call capital of friends. So somehow capital is not only some sort of a map, but some sort of a function as well. So we can look things up in a natural way in the dictionary, right? And because we are running things in interpreter, we get immediately the answer to this, right? So the answer to capital of friends is a string Paris. And notice something interesting that already has a name, right? res7. So the interpreter already created a local variable for us, and we can use it. How many people programmed in something like, I mean, even an interactive session of MATLAB, but definitely Mathematica, right? Good mathematician here. So in Mathematica tends to be exactly in the same way, right? You interactively type things, define things, whatever you do, and all the intermediate results get names, so you can go back and refer to them. It's very convenient. Now, of course, interpreted languages are nice. Scripting languages are nice, but they have the tendency to be quite slow. So the Scala designers decided to, in fact, support both a compiled mode and an interactive mode. Very few languages do this right. Okay? And usually languages acquire some sort of compilation much later in their life and is never good, right? So for example, MATLAB, in my opinion, doesn't have a particularly good way to compile things. It wants to be interactive, and then somehow they squeezed in some kind of a compiled version, but it's not quite right. Okay? It turns out that the Scala designers wanted to make Scala compilable from the beginning. Compilable, what exactly does it mean, compilable? In this circumstance, in particular, in general, right? That means you already map it to some kind of a much more efficient representation that can be executed much faster. Right? Now, Scala designers, and I give them a lot of credit for this, right? Scala designers took a really good decision when it comes to this. Okay? They decided to piggyback Scala on top of Java. So essentially, what the Scala designer wanted to do is fix Java. Put a lot of cool stuff into a Java-like language, remove all the not-so-cool stuff, compile against the bytecode that runs on top of the Java virtual machine to get all the benefits that you get from such a virtualization technique, right? What's one of the big benefits? All the tools that go from the Java virtual machine to extremely efficient implementation using a just-in-time compiler or whatever else is there are readily available. Actually, the connection between Scala and Java, and this is important for you when you're going to do your project, the interaction between Scala and Java is extremely tight. You can call Java classes, methods, whatever from Scala, and with some effort the other way around as well. Okay? So in a natural way, you can import Java libraries in Scala and call Java methods. and classes and instantiate things and so on and so forth. So to some extent, Scala makes itself compatible with Java, right? Now, why would you do this? Why would you piggyback a language on top of another language? It's the libraries, right? And I want you to understand this. When you design a new language, and it's very tempting to do so, right? When you design a new language, you have a big problem on your hands. The language is the core language. But there is so much more to a language. In particular, all those useful tools, all those libraries that can put things together, right? That allow you to do things in the language. Now, the Scala people took a very nice shortcut that said, hey, let's just use all the Java stuff out there. Great. They already brought the language from whatever, some curiosity. It looks cute, but it doesn't have anything interesting going for it, to, oh, we can do everything we can do in Java. And we can actually mix and match Java and Scala. Okay? You can form those .class files, which are the combined binary files, either in Java or in Scala, and put them together in a big jar and run all of that. Okay? So that was a really, really good decision, I believe, on the side of the Scala designers. And now Scala people like to think about it as the future of Java. Okay? All the things Java people want to insert in the language, they already have done it in Scala, but throughout all the ugly stuff. And I'll mention some of it. Oh, by the way, how many people here have done significant work in Java? Significant as in coded at least 1,000 lines of code or something like that. Right? OK. So I'll make Java references for those people that bother to raise the hand. OK? Now, Java actually draws a lot of inspiration from a series of languages, but more prominently from ML. Okay? How many people heard about ML? And especially, I mean, variants like OCaml. Right? So by the way, ML stands for meta language and was the darling of the languages research community for a very long time. For example, when I was a student at Cornell, right, for the type theory class, which was in fact some kind of a language class, we had to do projects in ML. And ML, it's a really cool language, but it has this problem that the libraries are not at the level of all the other libraries, and it seems somewhat esoteric. So what Scala designers did is took all the nice stuff from ML and mixed it up with the nice stuff from Java to get this kind of a mixed language. And you're going to see some of them, and they are really, really cool. Now, one thing about Scala that I want you to appreciate from the beginning, that it's a much more compact language than you're used to. I mean, it almost gets to the compactness of some of the advanced scripting languages of a very special purpose, right? So the fact that you see a program that's 10 lines of code doesn't mean you don't need a little bit of time to understand it because of how compact the language is. I'm going to point out just how nicely Scala does some of these things. Okay? Now, that's important for you. Why? Because when you write your program, a lot of your programs are going to fit on a single screen. And it's going to be, I believe, a shock to you to see how short some of these programs are going to be. I'm going to ask you to do assignments, and you're going to end up with 40 lines of code for something that seems like impossible to do without 2,000 lines of code in C, right? So this is my way of showing you the good life with the programming languages, right? So my purpose is not only to have something going on for this distributed systems class. I truly believe that Scala is the language of the future. Now, it's not good for everything, but it's good for an amazing number of things. And I'll point out throughout the class and some of them today of why I believe that's true. OK? Good. So I'm not going to go through this. Talks to Java in a native way. And whatever Java talks to, Scala talks to through the Java interface. In particular, C. Right? Java has a bridge to C, native functions and whatnot. Scala can piggyback on top of that. Okay? Performance on par with Java. Now, to some extent, I've seen numbers that show that the Scala performance is better. And this is somewhat strange. Right? It's essentially a side effect of the fact that you have more information because of the functional programming part that's prominent in Scala. And that's more optimizable, at least under certain circumstances. Okay? Okay? Now, and I do want you to understand this from the beginning, because once you understand this core concept, it's easy to understand how the language ticks, right? So the Scala designers, like the ML designers, are obsessed by cleanness of mechanisms. They have very few mechanisms, but these mechanisms are very, very powerful, right? So Scala is very big on compositionality. You can do smaller things and compose them in a clean way. Almost anything can be composed with anything. So it's a language that doesn't really have too many exceptions. So let me give you an idea of an exception, of a breakage of the rule that is, in the end, a nightmare if you do large-scale Java programming. Is, right, in Java, everything is an object, right? Except the basic types. So ints, doubles, the native types are not objects. They don't behave like objects. They have their own set of rules, and they create their own set of math, right? In Scala, those things are objects as well. Why not make them objects? Why not treat them like native things? Now, you deal with any issues related to performance when you compile, but not in the semantic you expose to the user. And that's really the mantra in Scala. Okay? So a lot of the things that are very cumbersome in Java, they become very straightforward in Scala. And to some extent, a lot of things that are cumbersome in other languages like C++ and whatnot. Right? Right? We'll go through this, but one prominent example is this idea of a trait. By the way, the traits make it into all the modern languages. C++ started to have traits. Java wants to have traits. Traits are basically characteristics that are parts of an interface. Right? So you remember from Java, you can define an interface and then an implementation of the interface. Right? And then you somehow can inherit from interface. It's not clear why that is. These guys cleaned it up. They say it's traits. So, right? So a trait can be, oh, you have something like an output medium or some kind of a property. And you can say, hey, this class that I want to define has this trait and this trait and this trait. And I think my iPad is really annoyed. OK, sorry about this. I have to remember to keep on doing something with the screen, right? So traits, a very clean way. And they have a nice way to mix up traits. It's called mix-in types. You say a little bit of this, and then inherit this from the class. And that's how I implement things. A much, much more cleaner interface than Java. So very few rules, very powerful, highly composable. Okay? Right? So this might suggest, and these guys really want to run away from this, that Java is some kind of a kitchen sink language. Now, how many people heard about Ada? How many people know the history of Ada? Why am I mentioning Ada suddenly? Why am I jumping up and down? Because Ada is a kitchen sink language. Okay, so the story goes like this, right? In about 1980, Department of Defense realized that they are using about 400 languages. And they said, hey, let's design one language to rule them all. Okay? And they formed a big committee. And the committee came up with a set of features that everybody inside the Department of Defense would have liked to use in a language. And a language specification, they called it Ada after Ada Lovelace, which was basically the first programmer. She wrote the first program for Charles Babbage analytical engine, right? Which was never really finished. It's the first non-executed program. Okay, so, okay, fine, big committee, formed the language. The language specification was so complicated, the first full implementation of Ada popped up only 15 years later, okay, in 95, right? So now that's a kitchen sink language. It had everything that anybody wanted, but it was so late that nobody is really using Ada for anything. So Scala is trying not to be that. But by relaxing that function call, it can simulate that it can do some of the kitchen sink stuff, even though in the end the rules are very simple. So remember, when you see a Scala program, things are in fact basic mechanisms composed in a very clean way. So it's always clean. You just have to look for that cleanness. Once you get the cleanness, the language is relatively easy, right? So broad comparison with Scala, right? You have a pure object system, no more basic types that are special. You have operator overloading, right, in a very, very nice way. Actually, operators are treated like functions and functions like operators. This is really the relaxation I mentioned. Which, if you think about it, it makes sense, right? Why would you treat the operators in a special way? Because C++ decided to do so. C++ has a mess with the operators, right? So Scala tries to straighten it up and says, they're all functions. Operator functions, they're all functions. And you can call a function like an operator like function. But it makes sense to call a function like an operator only essentially if it has two arguments, because otherwise it doesn't quite look like an operator. So a function with two arguments can be called like an operator, one or two functions. It's either the unary or binary version of it. And if it has more than two arguments, then you have to use the normal function call. Okay? It's optional to use the infix notation for a function, right? But you can use it, and that can make actually things a lot more legible. It's interesting. Okay? Closures. So closures are all over the place in JavaScript, right? We are going to come back to these things, right? Anybody has any idea what closures are? Right, so I got here one possible answer, which is an anonymous function. Now, by the way, anonymous functions are called lambda functions, right? Usually in the language. That's because of the language people. By the way, the lambda functions were introduced far before any programming language was introduced. Why am I telling you all these things? Because everything is connected with everything, right? Lambda functions are actually a competing universal model that competes with the Turing machines, right? Lambda calculus was introduced by Church in the 30s as an alternative to something that can compute anything, right? So the idea of a lambda something was introduced well before programming languages were fashionable, right? It was, in fact, a universal programming language. By the way, it's extremely cumbersome. And to a large extent, you can think of it as extremely crappy, but it can do everything, right? It's much worse than a Turing machine. A Turing machine at least has something that moves, right? The lambda calculus has nothing except x and lambda, right? But it can do everything, all right? So closures are really more powerful than the lambda functions. Are not only anonymous functions. I'm going to come back to this. But they can actually access variables in the surroundings where they are defined. So some sort of a partial function that uses as global variables the local variables in the environment in which it's embedded. So this actually gives you some super, super cool stuff you can do. And this is why JavaScript programming looks crazy on portions, because it makes use of these closures all over the place. Right? So we're going to have some examples. Now, by the way, all of these abstractions have to be treated with care. Any abstraction, if abused, is going to produce impossible to read code. I want you to understand that. It doesn't matter how clean the language is. You can always go nuts and produce something that can't be deciphered. Some languages produce in a much more natural way impossible to read code, like Perl. Right? So one of the jokes I found on the internet was why there are no obfuscated code competitions in Perl. Because everybody would win. It's just a cryptic language, right? Just crazy language. Scala tries to be the opposite, but try not to abuse the abstractions, okay? Okay, the mixin, this replaces that inheritance, right? Mixin means take these traits, add all of those characteristics to this class, right? Makes a lot more sense because it's a way to compose things as opposed to some mysterious thing, right? Existential types, we're going to see later, abstract types, right? What exactly are these abstract types? Why would you do abstract types? Now, in general, what you want to have in a language is some sort of templating, because it tends to be very powerful. You want to define, for example, the notion of a list or a map. We've seen the map. You want to define a map, let's say from some kind of a key, that's a string, to values, but you want the values to be very generic if possible, right? Now, you can do that in very inefficient ways. For example, having a generic object and then it can link to anything. But it would be nice to have so-called typed dictionaries that always go, let's say, from a string to a specific type. Now, how would you define that? Well, you can always do your own definition for every type you introduce, but that's insane. So this is why templates were introduced in C++, to have some generic mechanism to say, hey, use this code, but replace this type by this specific instance of it, and then figure out the rest. Right? Scala has that built into the language in a much, much nicer way than, let's say, C++ has. Right? The C++ template mechanism, it's just insane, right? I mean, after 20 years of programming in C++, I still hate it, right? Right? But Scala looks much cleaner. We're going to see some examples, okay? Pattern matching, okay? Now, pattern matching itself is worth, examples to follow, but pattern matching itself is worth switching to a language like this, right? Once you get used to it, there's nothing like it, right? Now, pattern matching in Scala, we're going to see exactly what this means. But pattern matching in Scala comes from ML. Pattern matching in ML comes from languages like Prolog. How many of you heard about Prolog? So what's this Prolog thing? It's some sort of logical programming language. Well, not quite. Okay? It does so much more than that. But in principle, it's the first language that introduced on a large scale this idea that you have patterns, structures. You say, if the structure is kind of like this, do this, right? And that's inherited with a nicer syntax through ML in Scala. And it makes the code extremely legible, right? So I would strongly encourage you to take advantage of things like this in the language, because the code is much, much, much better to look at, to debug. And there's almost no debugging, actually, to be done, okay? All right. So Martin has this cheat sheet here, right? Java is like this, Scala is like this. Now, let me mention something important, and that already makes it much easier to read Scala programs. Types in a language like C or C++ come in front of the object, right? You have int, function, int of x. Well, the Scala, so I do want you to understand, this is why I'm explaining so much connection with other languages. I do want you to understand that nothing is created in a vacuum. And people always have a certain inspiration, and they set certain standards. So ML had a really cool way to deal with the types. Not only had a very nice way to express the types, that makes more sense than the C way. The C way, it's insane in itself, especially when you have pointers and reference or whatever it's involved, right? C and C++ way. So ML had a much nicer way to express types, but had something much more interesting than that, something called type inference. Anybody has any idea what type inference is?
Basically infers the type that you need to have.
Right. So types are annoying. Okay, how many of you have written, for example, a C++ program in which you try to use a library, right, and use one of those STL types in which the template argument of the STL type had 5 arguments, and the name of the type was about yay big, right? And every time you had to go and look back in your code to see what that type was, to the point that at some point you said, hey, you know what? Let's use that nice facility in C++ to say type def this type and give it some sane name because I'm tired of it, right? By the way, C++ is getting type inference features, already has some of them. And to some extent, as a programmer, you really feel that the compiler should know what the type of that is. I mean, you see me using it. How come you don't know the type? I mean, what could I be talking about? And this is what the type inference is all about, right? Allows you to say, yeah, whatever, you deal with the type. And it works in most circumstances, and it's a really powerful feature, right? It works in most circumstances. There are some exceptions. For example, recursive functions. It's very hard to figure out what the type of a recursive function is because the type inference mechanism can go in an infinite loop when it runs the algorithm. That's one of the reasons, right? So the language designers did in Scala, borrowing from the ML mechanisms, right, essentially have a very powerful type inference, which pretty much means that for the most part, you can omit the type. But then you have a syntax problem, okay? If the type is in front, then how would you define a variable for which you don't want to say what the type is and you want to let the type inference mechanism figure it out? Oops. Then you have another problem, okay? And the other problem is the fact that you would like a natural way to specify whether a value is constant or non-constant, right? I mean, first of all, why would you have constant values? Because they definitely make the compiler do a better job. Okay? But it's broader than that. Okay? In general, knowing that something doesn't change makes it much, much easier to allow different things, different threads, to use it. There is no danger there's going to be any conflict because it's read-only. Right? So one of the desired goals in Scala was make sure we can indicate whether a certain value is constant or not. Okay? So they did this by, I mean, first of all, the type is specified exactly if you don't want to use the type inference mechanism. The type is specified like in ML, namely a variable colon and then a type specifier, as opposed to put it in front. And you can actually use 2 ways to specify a variable, either var or val. Val means it's a constant value, immutable. We are going to come back to this. Var means it's a true variable. You can change the value, and if you change the value, somebody else can see that you changed the value. Now, obviously, if you do some kind of a multi-threaded programming, a val is no problem at all because the language won't allow you to change it. A var, it's problematic. It has to be protected by some kind of mutual exclusive region. Okay, so this is why they are troublesome. Okay. Now, the val itself can be troublesome because every time you want to use it into some other object, that object itself becomes immutable. Right? So immutable, it's exactly what the name suggests. You cannot change the structure. You can embed it into other structures and do other things, but you cannot change that specific object. Okay. Java code is int x. That's basically the mutable version that they borrowed from C, C++. Final string x. This is the const. I mean, it would be equivalent to some kind of a const something in C++, for example. Right? So just pay attention to those var, val. By the way, borrowed from ML as well. ML had some of these imperative features. So it allowed vars, which was argued that is not good for languages that want to be functional. By the way, what does a functional programming language mean? And Scala is, to a large extent, it can be functional. So what's a functional programming language? This is ideas that mathematicians had, right? A pure function is some kind of a manipulation that has no side effects. It can produce a value, but that's it. It's not allowed to influence the world in any other way except through the value it produces. It doesn't change anything. It doesn't even need the notion of a state. It's a pure transformation. For example, x squared, right? X goes into x squared. It's a pure transformation. But is print x a pure transformation? No, because it has to change the state of what goes on the screen. So you have to manipulate some sort of a state, the state of the pixels on the screen, right? So print x, not a pure function. X goes to x squared, a pure function. By the way, all modern compilers try to figure out if a function is pure or not, because if it's pure, it can be optimized much, much, much better. Actually, dealing with side effects is one of the hardest problems to deal with when you compile a language, okay? So Scala designers really wanted a lot of this functional programming to go on. It can be optimized better. The code is much cleaner. Side effects in any function are bound to create hard-to-understand scenarios, right? You look at the function. For example, imagine that x squared not only returns the square, but changes a global variable to remember what the last square was. You see this code all the time, right? Now, that can actually be very problematic, right? Because then you can think about, oh, I'm going to do a nice optimization. The nice optimization is going to be, if I have to square the number twice, hey, I can just access that global variable that already has the last square. Except that in the meantime, you had somebody else in another thread call x squared, and suddenly your side effect is not thread safe. Oops, right? So it's very important to keep as much as possible this functional flavor to a language. Now, a pure function programming languages are really annoying. So Scala people wanted to stay away from them. They allow imperative. Var, imperative. Val, very functional. Okay? Okay, expressions. Now, Scala has something really cool. Is this a so-called case expressions, right? Now, you do have some sort of a case expression, maybe not quite, in languages like C, right? A switch case statement. So now let me ask you a question, right? From your C days or C++ days. What's allowed for the case part in a case expression? All right. So now, right? I'm sorry?
Not an object.
Well, definitely not an object, but really in C++ it's just integers. But that's really annoying. Because why? Because suddenly we are forced to have enums, which happen to be some sort of fancy integers, everywhere. Right? So we are already given some sort of a recipe. You want to use a switch, fine. Use enums or pure integers. I'm not going to allow anything else. Right? The code is very hard to keep nice. Okay? Now, what would be the coolest thing ever? To say, oh, you know what? I have an object. And if the object happens to be, in this case, well, we don't have an example here. If the object happens to be, I don't know, an integer, then I want it to do this. If it happens to be a string, I want it to do this. Wouldn't that be cool? Well, Scala allows that. Now, how the language implements this is a different story. But actually, Scala allows much more than that. You can actually do very deep pattern matching in which you can specify even subpatterns. This comes from Prolog, right? So you can say, if you see a string that matches this string matching pattern, then you do this. If you see a string that matches this other pattern, do this. If you see an integer, you do this. Makes the code extremely readable. Okay? We're going to come back to this later. So the expression match and case, it's very powerful in Scala. Much more powerful than the switch statement in languages like Java or C++. Okay? Much, much more. And this makes the code extremely legible. So when you combine a very compact language together with the case expressions, and we're going to see this all over the place in Scala, it makes a very powerful compact language that's easy to read because it fits, almost everything fits on a single page, right? All right? Now, another very annoying thing, and this really bothers me because it's so cumbersome to implement, right? So you almost always in a language, so classes are nice, right? Classes specify a common interface that multiple objects are going to have, and then you can talk about instances of classes, right? You're all familiar with that. That's what I'm assuming. But you almost always want either static members of a class. So what exactly is a static member? This comes from C++. C++ people invented it, right? So what's a static member? I'm sorry.
Even after the lifetime of the value is over, I mean, even after it executes, the value is stored.
So it's actually not only that. So the definition I got is static members are members that exist even after the values are deleted. Well, they exist even before any value is created. Actually, static members just exist. Not only that, they are common for all elements of the class. So they have this weird aura attached to them with these weird rules. Well, the Scala designers took probably the best decision of them all, and you have to be aware of this because, by the way, even when you look at the Scala documentation, you're going to see two choices there. Do you mean the object or do you mean the class? So what they did is they realized that quite often you want either static members or, in general, to have a singleton for a class. One specific member of the class that always exists that does something. So literally what they said is, hey, why don't we call, we have two keywords. A class specifies the class definition, what all those objects do, and the object specifies that singleton, what this special guy can do, right? And by separating things out makes your life much, much, much easier. So anything that normally you would associate with a static goes into object that has the same name of the class. Anything that goes with all of the members of the class goes into the class itself. So by default, all classes in Scala can have a singleton. You just have to call it object sample and just have to tell me what that guy does. It's a very convenient way to do a very common thing, that singleton object. Okay? Right? Traits, I'm not going to go through this, right? They define interfaces. They could be abstract. So abstract means you specify some constraints on them, right? So you're basically just saying, for example, abstract method, it's something that maps a string into an int, but I'm not going to tell you what it is. It has to be defined later. So these are also ideas coming from these languages like Prolog, in which you can partially define something and let it hanging. It cannot be used until you fully instantiate it. Okay? So you can do some sort of a partial instantiation. In this case, it's very partial. Nothing is defined except the type of the function. Okay? Or this one is more specific. You say the concrete method maps a string. And notice that there is no return type. Type inference is going to kick in, right? Any function has a very clearly defined return type because Scala is a strongly typed language. What's a strongly typed language? Lots of big words today. So what's a weakly typed language? So let's vote on some languages, okay? So let's say something like, even Python. What's Python? Strongly typed or? Actually, usually you don't call them necessarily weakly typed languages. You call them dynamic typed languages. So what's a dynamic typed language? The type of an object, I'm sorry?
The type of object can be changed in runtime.
Right. So you can do weird stuff like x is equal to 2int of x. So x was a string, and you call the function toInt, and you take the value of x and put it into x, and now suddenly x is an int, even though it was a string before. Now that makes for very cute code, but also makes for not particularly efficient code. Why? You have to carry the type of an object with the object. So an object is not going to be only the value of the object. It's going to be the type of the object, and then all kinds of other things for good measure. Okay? So that adds a lot of ballast to the language. Yes?
Trait, I think it's comparable to abstract class in Java, local interface.
Trait is comparable with abstract class. The important thing to watch for in Scala is that it has much cleaner, better confined, and more basic definitions of everything, plus composing. The trouble with Java is it was derived from C++, and it did not remove all the problems in C++. Right? The trouble with C++ is it's a language designed by the C hackers to provide job security for C hackers. I mean, it's an indescribable language. I mean, don't get me wrong. It's the right language to do certain things. For example, high performance anything, right? But the language itself still puzzles me after 20 years. Anyway, Scala, much, much, much cleaner. And you're right. Okay, you're going to have to use these strings. So a strongly typed language is a language in which at every single point in a program, every variable has precisely one type, and the compiler can figure out exactly what type it has. Okay? So literally, and by the way, this is going to be really your only problem in Scala, your only major problem in Scala. It's nice to use the type inference. If the system cannot use the type inference, it will ask you for some types in there to figure out what the type, how to finish the type inference. And some of those messages are going to get annoying, especially when you use esoteric things like futures, okay, which I will touch upon a little bit, right? You use futures, you're going to get this very weird message saying that I can't quite figure out how to instantiate this type, and that's when you're going to hate Scala a little bit, but trust me, it's worth the effort, okay, to actually learn it. So in this circumstance, the return type, it's inferred. How possibly is it inferred? Well, you see, X is a string. You see a plus between a string and a field, and plus it's only supported for strings. You can look it up at what functions are defined, so you can actually infer that the result is in fact a string, right? Not to mention that the field itself, it's a string. How do we know it's a string? Look at how it's instantiated. Remember, the type of an object is fully determined at compile time. And because this constant will be automatically converted to a string, it's essentially a constant string. This is how Scala defines it. You know that you can infer immediately. Field, it's a string. X is a string. Plus is between strings, so the result is string. You look up it in the function, right? By the way, this type inference exists now in C++. They have a fancy name for it. It's called auto, right? So you can just put autos everywhere, and the compiler is going to try to figure out what is it that you want to do. And in particular, it's very good for variables. You can say auto x is equal to an expression. Amazing, especially when you have those ugly templates instantiated, right, in C++. It's my favorite new addition to the C++ in the C++ X11, okay, the auto thing. The GCC had a feature before called type def and type info and things like that that were not quite as good as auto. Okay, good. Right. So here is an interesting question, right? Now the slides are a little bit messed up, but not too much. So we have this capital, it's equal to map, US goes into Washington. What's this? What's this arrow? Now, usually in a language, that's some kind of a special keyword, special operator, some sort of a thing, right? Most languages would, in fact, for example, Python has this, will have a built-in dictionary type. Or PHP is like this, right? Has a built-in dictionary type that has its own little syntax, and then you have to hardwire it in the syntax of the language and whatnot. Well, it turns out that here, the map is completely in a library and uses no special anything in the Scala language. And this is, in fact, an operator. It's a library-defined operator. And essentially what that operator does is it forms a tuple. So it takes the two members at the left and at the right and bundles them into the tuple. A tuple is a basic type in Scala, right? If you take multiple values and you glue them together, that forms some kind of a generalization of the record, right? You're familiar with tuples. Most of them, I mean, most languages don't have a particularly good way to form tuples, but Scala does. Okay? So this is actually, I think a tuple is written with open brackets and comma-separated elements inside. So this, the US goes to Washington, it's equivalent to open bracket, US, comma, Washington. Okay? So this is basically some sort of syntax sugar. It's a very shallow function that does that. Okay? So you're going to see a lot of these things, and you can invent your own. And actually, the arrow can be anything that looks like a function. Right? So the arrow is really a function that takes two arguments and forms a single result that's of type tuple. Okay? Right? Right, so we talked about the type, right? The colon, it's used to specify type CS.
In the previous slide, inside the for loop, the arrow was like this side. I'm not able to get it.
No, but this is syntax for for.
Oh,
So that basically means C takes the value capital keys when you go over the for loop. But the for here is some kind of almost like a functional programming for. It feels more, so I mean, I'm going to ask you to go and delve into the language and so on. But because the language has a functional flavor, the for loops can look nicer. Right? The for loops in C, and any language derived from C, are a weird contortion of things, right, with their own weird rules. To a large extent, this 4 can be some sort of a function that goes over some map or some sort of a container and enumerates the elements in the container, and for each of them gives names to local variables, and then you can do something with the names. This is what most high-level, more script-like languages do. For example, this is, how many of you wrote anything in PHP, for example? But I mean, even in JavaScript it's true, right? So the syntax tends to be like this. You go over arrays. I mean, you have 4 each going over an array. Arrays are really dictionaries, for example, in PHP or in Python. OK. Let's skip over some of this. Right, so this is basically a more elaborate example, right? You have int, long, float, double. These are basic types. You might want to graduate to more advanced types. Why would you do that? Well, because the hardware starts to support very fancy types. For example, I just found out a couple of weeks back that the new GCC compiler supports 128-bit floats. That's great, by the way, if you want to do very large-scale data processing, because otherwise you can overflow even a 80-bit float, the double, right? So 128 is perfect. But then, OK, fine, how am I going to use a 128-bit float? Do you know, for example, how languages like C++ do this? Well, languages like C++ are weird. They have connections with assembly, right? So worst comes to worst, you just generate some assembly instructions at the lowest level and be done with it. Okay? And this is literally how you do things. But it's important to add support for things like this in the language in a more library way rather than put them in the core language, right? So this is an example of how you could support types. But the problem is, in Java, these basic types that are natively supported are treated differently than anything derived from object, any object-like type, right? But not so in Scala. And you can go through this example. I don't quite have time to go through it, right? For example, look at this. This is a factorial function defined on this type, big int, which still needs to be defined, right? In this case, there is a full type specification. You say the input is a single value, x of type big int, and returns big int. It makes it so much nicer to say, you take this as an input, and then this is a type of the output, as opposed to the C way in which the return is somewhere, and it's just all over the place, right? And notice you just need a def. Def defines a function. That's similar to Python, I think, right? Var, val, do the constant, I mean the non-constant, mutable and immutable variables. Very nice thing, right? Also, the Scala has another feature that's borrowed from functional programming languages, which is the last statement in the body of a function determines the return. That makes for more compact code in which you don't write return. Whatever is the last thing you did, that's the thing that determines the value, right? In this case, what's that? It's this if statement that essentially has two branches. The one, if you go left, and the x times factorial x minus 1 if you go right. Okay? And no need to say return this. Return is optional, really. Okay? If you put no return in the body of a function, the last statement is the return. By the way, that's true in JavaScript, and that's true in PHP. Right? So these guys were paying attention to how people like to use languages. Okay? Much uglier version in Java. Okay? The example is more elaborate, right? The plus, it's really defined like any other function. Why not? As long as the language can figure out when you mean function, and it can, because if you put def, that means you're defining a function. Actually, C and C++ are very funny with this. It's quite hard to figure out what is it that you're defining there, because you can use those brackets to do other things, not only define functions, right? It's so much nicer if you have a nice keyword that says, hey, I'm defining a function, I'm not doing anything else, right? I mean, for example, JavaScript has that. It's called function, and this is that, right? Control structures. This is interesting, and this is what they mean by a scalable language. You can define your own control structures. For example, this using. Now, in order to do that, right, you need some magic. Let me see the more elaborate example. Okay, so this is an interesting example. Okay, so let's look at this. Now, you're going to notice something that's similar actually to Java, but Java is too slow to do this, and it's similar but with a different syntax in C++. That means a template definition of a function. So what's really a template? Did you ever ask yourself? So what are you doing when you're defining a template? For example, the templating in C++ or Java or some other languages. So what's the difference between a normal function and a templating function? The templating function is a recipe to generate functions. A template cannot run. It needs to be instantiated to become a normal function, right? So it's really some sort of a pattern, some sort of a, if you want, yes, a recipe. That's a good way, right? So you say, if you replace this by this and this by this and this by this, then you can get something that looks like a normal function. So actually, the easiest way to think about it is a form of code generation. The compiler internally, if you have a template, will replace the template variable with a specific type, write the code as if you would write it, but now with the type plugged in. It's exactly the way you specified, and then go and compile it like any other normal function. But, OK, this sounds great, but the question is, what's the language to specify these templates, and what can you do in that language? OK? And what can you express in that language? So usually the template languages are sub-languages within the big language. And sometimes they are added much later, and they look much stranger, right? The Scala designers decided to design the templating mechanism at the same time as the rest of the language, so it actually makes sense. And by the way, they borrowed from the so-called alpha types in ML. Okay? Alpha types are generic types in ML. Okay? It's a very fancy version of this templating mechanism. Now, not to scare developers, Scala people did a very good job at not scaring people. ML is a very scary language. It's full of this extremely heavyweight terminology, right? I mean, literally, to understand fully what alpha types do in ML, you have to take an advanced class in type theory, okay, where they talk about the foundation of type inference and whatnot. Scala people still do that, but try to stay away from these fancy things like alpha types, okay? But they call them template types. And this is really a template specification. You say, I'm defining a function, but it's really a template, right? I know it's a template because of the square bracket. It's going to depend on a parameter t. And by the way, this is a restriction on t. So this less than colon, it's special notation only when you're describing templates to say this is a restriction. And in this case, it specifies that the type t must have the method close. Now, for example, in C++, that's implicit by the way you use the template, right? You say, let's call the template this and this and this, and then let's use it. And when you compile the code, it explodes and says, hey, you're supposed to have this method, and you don't have it. Sometimes it's hard to determine what's going on, and you get really big messages, right? In Scala, because you have these constraints on the type from the beginning, it's much easier to produce nice error messages and say, hey, you must have close. And by the way, you can put here things that you know you need in the future. So it's not only a use base, but it's future-proof. I told you must have close. Even if I don't use it, you must have close. Otherwise, I don't allow you to be instantiated in this way. Okay? Now, there is a very interesting type in Scala. And am I over time? Well, we have 2 hours anyway, so we'll take a break in a different way. So I mentioned those closures. The closures themselves are first-class citizens. Actually, functions are first-class citizens. I'm going to mention in a second precisely what this means. But closures are first-class citizens. So the closure type is this unit. So this function is actually interesting because it essentially, what you're essentially saying is that you take as an argument for this using a block that takes some type into this closure. So it takes some kind of a closure argument. And we're going to see this all over the place in Scala. Okay? You have they are almost kind of a meta function, right? They add something for themselves. They take a closure, and they embed that closure into bigger code to do bigger things. OK? All right. Now, I'll let you go over this and try to figure out what it does. And you're going to have to do some of these things. And one of the things that the Scala people are most proud of is this break and continue story. They don't support break and continue. It's like, you don't need them. Well, I mean, how many people here have used break and continue in their code? So now how upset would you be if I tell you you don't have break and continue? Well, I mean, first of all, break and continue makes for not so nice code. Okay? Essentially, when you write that code, you're hacking. You're hacking a lot. I mean, that's the first argument. But the second argument, and this is kind of the ultimate argument, is it's easy to provide break and continue functionality in the language, but you provide it in a library. So this is how you know you have a very powerful language. If a lot of things that normally would have to be built into the language are now in libraries, you say, yeah, do it in a library. And you can do it in a library. This is strange. You can do it in a library And this is an example of how you could call it, right? So let's look at this code. You say breakable, and then some kind of an open bracket, and a piece of code that uses break in here. Now, how would this work? What exactly is going on in here? Well, what's happening is, so the big question here is what's breakable? Right? So what's breakable? Well, it turns out that breakable is a function. But breakable takes as an argument a closure. Now, how do we define a closure in general in ML? And this is not only an anonymous piece of code, but actually can borrow from things that come from outside variables in the local context, right? If you do open curly bracket, a piece of code, close curly bracket, that in itself already is a closure. So the way the language treats it is, oh, I already have this abstract object called the closure that I can actually pass to this function that takes as input closures, right? So we can look at a breakable, right? So this is how you could define it, right? So this is define breakable, right? Takes as an argument one of the, it takes as an argument an input, and the type of the input can be input, and it's in fact unit. Takes a closure and produces a closure, right? And what closure does it produce? Well, it's going to put the following code. Starts a try block, then puts the argument, which is the operand, the full closure that you wrote, puts it in, and then a catch, and it says, well, if the expression, this is exceptions, right? If the exception was break exception, then you return nothing. Otherwise, you just return the normal result of the closure. It's very, very compact language. And then what does the function break do? Just throws the exception. Okay? So now these kind of features are extremely advanced features. This almost looks like code generation. You're composing code with other code to make bigger code, but in a different way than calling a function. Right? So these closures, because they can actually borrow from the context, notice that you don't call it even like a function. You say, it's as if you say, take that code and dump it here. Right? It's a very, very powerful feature. So not so much that you really need to do this break and continue, which is probably not something you should do in your code too often, but it gives an example of how powerful the language itself is. Okay? Now let me make a suggestion. Since the clock is not stopping, I don't really need a break. We can go on and we just stop earlier and then we have a bigger break later. Is that fine? All right. Good. So let's not go through all of these things. I'm going to let you actually go over this, see exactly what functional means, have fun with it. My advice, by the way, is Google. Okay? There are there are many ways to Google. One of them is Google Code. Go on Google Code and find projects written in Scala. Google for Scala code or whatever, and find many examples. I mean, the best way to learn programming is to see good examples of code written in that program. What I'm not asking you to do is read the definition of the language, the abstract definition of the language, and suddenly write good programs. All of these languages come with, language designers had a certain thing in mind. The language doesn't restrict you to do the nice organization for it, but if you see some examples, you say, ah, that's a much, much neater way to tackle things, right? So just Google. Another suggestion I have is, as you're going to Google, you're going to bump into interesting resources about Scala or other things for the class. Throw them on the mailing list, right? Anything that helps you learn. So anything that's not a solution to a specific problem I asked in class, it's something that other people might be interested on the mailing list. You find a very good tutorial on Scala, throw it in. You find a book that's Creative Commons book. So I don't want to see proprietary books that are shared illegally on the mailing list. It's not good, okay? But there are so many resources out there, right? You have snippets of code. For example, some people are going to say, hey, how do you do this in Scala? You can write snippets of code. Again, if they are not really a significant part of the solution, that's fine. And I want you to use the mailing list as some kind of a social network to learn Scala, right? And distributed systems in general. Right? The goal of this class is really for you to learn and not necessarily for you to get a grade, which you will, but it's a kind of a side effect. Right? Right. So many features, partial functions and whatnot. I mean, it's a really cool language. Right? Now, what I do want to spend time on, but I want to switch to the other slides, is this actor stuff. Okay? This is much more important for me in this class. Right? So hopefully you're excited now about Scala. You're going to go learn Scala, look at all kinds of cool examples. Okay? Let's switch to actors, and we're going to see more examples of those case classes, which are very interesting. Okay. All right. So actors. So I'm going to give you a better introduction to these actors. Let me see exactly what I have on these slides, because this guy already thought about some good introduction. Okay. Right. So this is kind of the best introduction of them all. So this class is about distributed systems. All right. One thing that I suggested, and I want to follow up on it throughout the class, is even if you just have multiple cores in a single machine, you might as well call it a distributed system. And this sounds a little bit like, hey, what are you talking about? Distributed systems are about networking, going to other machines, and doing stuff like this. But if you do treat a multi-core machine like a distributed system, you're going to get much better performance of that multi-core machine, right? Now, this is very counterintuitive, because you have the feeling that, hey, if I work on the same machine, I could do so much more stuff, right? Share the memory, everything is instantaneous and whatnot. But it turns out that all of those ways are just a very long rope you can use to hang yourself in very interesting ways, right? So you get performance, but you lose almost anything else, okay? Now, interestingly, this actor model will allow you to make the rope much shorter to the point that it's not usable, okay? So to a large extent, the actor model allows you to pretend you don't have all of those great facilities that are all pitfalls. And you pretend that you don't have shared memory, and you pretend that you have to talk to somebody as if they are at the end of the world, even though it's simply just another little object that lives in the same memory space. And that turns out to be very healthy and produces much better programs. And to a large extent, produces more efficient programs. I'll come back to this later in class, right? Efficiency is a very tricky business. In the database implementation class, I talk extensively about it. Smartness is actually in the way of efficiency almost all the time on modern architectures. Okay, I'm not going to go into all the details, but the actor model can actually produce very efficient code. You're going to convince yourself by doing the first project that this is true. Okay, so let's look at this slide. So, I mean, this is really what's going on now. So, my favorite question is, how many people have a uniprocessor cell phone? I asked some of these questions maybe last time. A cell phone that doesn't have at least 2 cores. Well, Samsung has now 4 cores in their cell phones. Okay, right. Is it a smartphone? Maybe a very old one. I've heard that you can, if you sign up for a new plan, they give you a new phone for free now that has 2 cores, right? So why do we have all these cores? So what's the deal with the cores? Who asked for cores in the first place, right? So what happened? Well, what happened, they ran out of other things to do, okay? So how many of you remember the frequency wars in which my CPU is faster than yours because it has more gigahertz, right? You meet your friend on the street and say, how many gigahertz does your computer have, right? So how many gigahertz does your computer have? How many people know how many gigahertz their computer has? So roughly. 2.6. Now, a 2.6 gigahertz processor popped up in about 2003. Right? Now, if you look at the frequency before, it was going very nicely up. Anybody has any idea in 85, when the 386 was introduced, what was the frequency at which the 386 was running initially? 40 megahertz? Megahertz is 1,000 times more than gigahertz, right? So we are talking about 100 times improvement in the clock speed since 85. It was constantly going up very nicely, to such a great extent that when Microsoft was designing a new operating system, they were designing for the clock frequency 2 years ahead, right? It's like, hey, the frequency is going to double anyway. So we can have this really inefficient operating system that's going to run just right on the frequencies 2 years from now, right? Literally, they were doing this. Okay, caught up with them lately, but right? So what happened in about 2002, 2003? They ran out of gigahertz. Why? Who here is in EE department? So what happened with the frequency? Right, so the frequency has a nasty habit of not even bothering to go linearly with, I mean, the power requirement is not even linear in the frequency, right? And now simply processors are too hot, right? That's the problem. You go a lot, I mean, you can do How many people have liquid cooling on their desktop? Some gamers do, right? They sell this very fancy stuff in which you can overclock the processor. I've heard about 5 gigahertz processors. It was sold as a 2-point-something gigahertz processor, and it runs at 5. You just put enough cooling, and maybe you can manage the process, right? So good, that's out. The frequency doesn't go out because it becomes impossible to control the power dissipation. It's not so much you can't put enough power. We can do that, okay? More than, I mean, you can upgrade your power supply in the worst way, in the worst case, right? The big problem is where does all that energy goes, and that's very problematic, okay? So frequency leveled up, but Moore's law, who knows what Moore's law is? Well, the founder of Intel made an interesting observation that we are going to be busy forever because we are going to essentially double the number of processors every 18 months, number of transistors. He never said anything about the frequency, but here's the kicker, and people can confirm this. If, at least for a while, if you put smaller transistors, you could raise the frequency until the power caught up with you, okay? So that was great. By the way, so in 2002, the frequency wars stopped. The manufacturers even didn't, stop bothering indicating the frequency for a processor and came up with other gimmicks to sell them, right? So what happens in 2002? We already have a decade. Well, the number of transistors kept on going up. Now, for a while, they tried to use the transistors to make the processor smarter. That gives you marginal improvement, right? You make the logic much more complicated, you get 2% performance improvement. Nobody is going to notice. Who's going to buy a processor because it's 2% faster than another one? Forget about it. So then they started a new game, which is let's put multiple brains, multiple cores on the same die, right? Now we got to the level where on a single die, well, I think Intel can squeeze now 10, right? 10 cores. AMD likes to put 8, but likes to put 2 of those dies in a single packaging, right? So you can buy now a processor that has 16 cores. This is for the high-performance general-purpose processors. If you go to Intel Phi, they already have 50, and there is a company, as somebody mentioned last time, somewhere around MIT that puts 64 and wants to put some 1,024 or something like that on a single core. OK, great, but what can you do with all of those cores? Right, so if you took another class with me, I'm sorry about this joke, but in about 2005, 2006, when the multi-core started to pop up, dual cores, quad cores, so I've heard this commercial on radio for why you should buy a 4-core desktop, because you can run a web browser, email, and something else at the same time. And that's only 3 things, and you have 4 cores. Actually, my perfect application for why you need multiple cores is because you can have, if you have n cores, you can have n-1 infinite loops going on in parallel, and 1 is left to do some real work. Of course, you don't need multiple cores to do concurrency, and we're going to talk about that, right? But the fact of the matter is very few applications use multiple cores in any reasonable way, right? You can buy an 8-core processor, and it still doesn't run faster than a 1-core processor when it runs the word processor or something. It's still slow when it does some of the things, right? So why is that the case? We don't have smart programmers. Well, the problem is the abstraction, okay? We had multi-threading since the 70s, but it's very hard to program against the multi-threading. Now, something happened. And something that happened, by the way, this is Amdahl's law, and it's famous for a limiting factor on how much speed up you can get, depending on how many processors you have, right? So these curves are percent, how big the speed up is, the theoretical speed up, in terms of the number of processors, in terms of how much parallelism do you have in your code. So if you have only 50% parallelism in your code, then you reach maximum performance at 8 cores. Anything beyond 8 cores, even if you have perfect communication, it's out of the window, right? Even at 95% parallel code, you're still limited at the factor of 20 in scalability, even if you have 65,000 cores. So that's really, really bad, okay? So you need to achieve much higher than 95% parallelism in your code, okay? All right. Parallelism is hard in any language. Race conditions are truly awful. It doesn't matter how many gizmos you add to the language, it's still very, very hard. And it's very hard because it's very hard to reason about it. If you write a homework assignment in which you say, hey, I have 3 threads and we do something with 3 threads, hey, that looks nice. But a real application might have something like 400 threads. I have, for example, a database engine that likes to throw out 400 threads. Now, how do you think about the interaction between 400 threads? What do those guys do? If you're looking at mutual exclusion regions in a normal sense and so on, you can't tell what the system does. The actor model makes it much, much, much better, right? How? Well, these are the pitfalls. Well, it allows you to have a very intuitive way to think about things. Yeah, you pretend that multiple pieces of the code cannot talk directly to each other. They have to do it through a formal mechanism. It's called messaging, right? And each of them have a life of their own. They live on their own, and they interact on their own. And all you have to do is specify what is it that they do. It's as if you write the script for actors, right? You say, hey, you only have to worry about these other 2 actors. And if you get the message from this one, you do this, and maybe you send the message to this guy. And you don't care about all the other 400 actors do. You just watch your own little world. And then it's much, much easier to write very complex software in this way, because you just write small compartments. You're going to write the behavior of all of these separate actors. Okay? The actor model helps. Another thing that helps in a big way is this immutable data structures. Okay? So immutable data structures, as I mentioned before, is that val in the language in Scala means you're not allowed to change the data structure. You can build other data structures out of it, but they cannot be changed. You can actually change them, but you have to then break it apart and reconstruct it for somebody else to change it. These immutable data types, by the way, appeared about at the same time as the mutable ones, right? 2 of the first languages were Fortran, which is the parent language of all imperative languages, and Lisp, which is the parent language of all the functional languages. Lisp only had immutable data structures initially. And then they started to add a little bit of mutable there because people started to cry. Fortran had only mutable data structure. Everything was a location in memory, and you could do whatever you wanted with it, right? So very, very different approaches. But immutable means you don't have to protect them when you have multi-threading. Now, you do want to allow mutable, but in an actor model, to do so, you can do so cleanly by saying anything that's mutable belongs to a single actor. Now, there is a variation on the actor model that I use in my own database engine in which you add something called swapping paradigm, which I will describe maybe next time just to give you an idea of what can be done, in which you can have mutable data structures and still not have concurrency issues, right? But I'm not going to go into it right now. But it creates other limitations, not big limitations. None of them are big limitations, but it takes a certain discipline. Okay? Right, so actor model was formalized in 1973. But, I mean, this is the problem with mathematicians, I'm sorry. But when they formalize something, they really formalize something. So the original actor model essentially said, hey, if you have actors, you don't need anything else, including for loops. So then an interesting question was, how do you do for loops using a pure actor model? Well, you do this. You have an actor that runs the current iteration and then creates another actor that's going to run the next iteration, which creates another actor that runs the next iteration. This is insane. This is not the way to use the actor model. So what's good about actor model is the fact that it's a nice abstraction. You have this independent entity that can exchange messages with other things. What's bad about the original abstract actor model is that it went all the way and it can't be implemented in an efficient way. So you want to have imperative behavior within the actor, but only these message exchanges for the actors to interact with each other. Okay? Well, other people came along, right, Gal, Aha, right, in the mid-80s and said, that's insane, let's do a more reasonable language. And they designed Erlang. Okay? Erlang was designed in the 1980s. And by the way, Erlang is heavily based on Prolog. It's basically Prolog plus actors. And introduces very, very lightweight actors. And Ericsson, right, the research group at Ericsson designed this. Ericsson said, hey, let's use this to write telecom code. Well, they pulled off something amazing, right? So they designed a system that has 99.999999% uptime with actors. Now, if that doesn't show to the world that actors are valuable, I don't know what is. How did they achieve that? Well, there are 2 ways to achieve that, is to have people that write code that has absolutely no bugs. Well, they don't exist, so you can dismiss that. Or to write code that fixes itself. Now imagine, what does fixes itself mean? Well, in general, to write code that repairs itself, it's such a complex thing you don't even know where to start. But it turns out that it's relatively easy with actors. So the approach with Ericsson took with actors is the following. Hey, we're going to create low-level actors that do the work. Then supervisors actors that just watch how these guys do the work, and in particular monitor these guys. If one of them notices that an actor died, creates another actor in place, right? In fact, this mimics the way the humans organize any large-scale activity, right? Writing perfect code is equivalent to just having workers in a factory, nobody supervising them and doing anything, and none of them ever getting sick, and everything just working. It's not happening. It's not happening for many reasons. It has nothing to do with how perfect the code is. The machine can run amok because an alpha particle hit a memory location and flipped a bit. I mean, things happen. Power goes on, all kinds of things like this, right? So the actor models approach is really do this kind of do work and monitor, but then you can have watchers for the watchers, right? So supervisors supervise smaller groups, they have supervisors larger groups, and maybe a committee at the top, so that even if half the members of the committee die at the same time, the committee is still working. By the way, distributed systems are a lot about these things. So the core principles and the core ideas in distributed systems, how you make things failure resistant and so on, are very similar to what Ericsson did with the actors. So in a natural way, these actors match any endeavor in distributed systems. You want to have somebody watching what particular processes do. Hey, create another actor that just watches them. What does it mean to watch another actor? How do you watch another actor? You could ask the actor to report regularly, and if it doesn't, you say send some more brutal messages, and in the end you say, hey, it died, or something, right? So we're going to talk extensively about this kind of techniques. But the important thing is the actor model has the means to do so, right? So, for example, if a supervisor, you keep track, I supervise 10 actors, and I keep track what's the last time I heard from them. If I have more than half a second since hearing from them, I'm going to panic and start doing something, right? Then the actor that's supposed to do some work, well, it's supposed to regularly send messages, right? Why half a second? Because computers are fast. Humans usually report only once a day. Yes? Right. So, good. So let's talk a little bit about this, even at the expense of, yeah, I will finish this. It's not too many slides to go from. Right. So whenever you're talking about fancy features, abstractions, or whatever you want to call them, you say, whoa, 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 it's going to be slow. Okay? Now, that's always a legitimate concern. And definitely, if you're writing for loops using actors, then you should be worried about slowness. But in your first assignment, I'm going to essentially ask you to determine what the good breakpoint is. So let's imagine the following situation, that I have workers, and this really describes your first assignment. You have workers, and I have the supervisor. The supervisor, basically, the role of the supervisor is going to be just to give work to the workers. Maybe monitor them, but definitely say, right, we need to accomplish something big. For example, let's suppose we want to break encryption keys, right? If we want to break encryption keys, let's think about this. We want to break encryption keys. Well, we first need some workers that when given a candidate key and maybe some kind of a hash, tries to figure out if this key corresponds to this hash. And if yes, hey, we have a match. So that's a brute force attack on security, right? So one specific thing you can encode in one of these actors is, hey, I'll send you a message with a key and a hash, and you compute whether the key matches the hash. Now, if that's the case, what do you think? The code is going to run fast or not? Well, so let's put some numbers in there. So suppose in order to determine if a key matches a hash, I need a microsecond. Right? Now, then you start asking questions like this, right? If it takes a microsecond, that means every worker can do 1 million of them in a second, right? Now, let's say we have 16 workers. I have 16 cores. It better be the case that you can deliver 16 million messages per second, even not given any other overhead, because otherwise the bottleneck is going to be distributing messages. So it's going to start looking not so good if you go too low level. And by the way, a microsecond is very generous for breaking one of those keys. You can actually compute those hashes much, much, much faster, and then suddenly you're in trouble, right? But to a large extent, that's a very naive way to do the work. I mean, imagine as if, right? So this is the best way to realize whether you're doing the right thing with the actor model or not. How many of you know about how the logarithm tables were computed in the 1600s when Napier came up with the idea that you can do multiplication using addition? Right? Well, they were done by hand, right? I mean, they had people. To compute the tables in the 19th century, they literally were employing up to 10,000 people computing by hand and with not sliding rules. That was already an amazing invention, right? And that's a 20th century invention. It was abacus and by hand, right? So imagine now you have 10,000 people computing by hand, but each of them, for example, they were employing the so-called savants, right? People that had very bad social skills or non-existent social skills, but they could do mathematical computations, right? Napier actually used a famous savant to actually compute his tables. It took only 20 years for Napier to compute his tables because he only had one savant, right? So you're the boss of all of these people, and you have to say, OK, when you're done with your computation, raise your hand. That means send me a message and say, I want one more. You have to send me back the previous result because I'm going to put it nicely in a table, right? And then you raise your hand and I'll send you another one. Now, if everybody finishes in 1 second, human scale, right? Not 1 second, let's say 5 seconds. You have fast people, they compute one of those entries in 5 seconds. You have 10,000 of them. You go insane by just distributing a message to those guys. I mean, you have to be a really fast human being to deal with it. Even if you put a minute, 20,000 people, it's going to be a disaster, right? So how would you organize this at the level of accomplishing this with human beings? Well, first of all, you wouldn't have an overall boss, right? You would have separate departments, maybe, or separate groups, a boss over each group. But even a boss itself, even if you're watching only 10 people, you say, hey, I'm not going to give you a computation to do. I'll give you a block of computations. It's, hey, you're responsible for whatever number, 1,025,000 to 1,105,000, right? When you do that, bother me. That way, more work gets done, messages are bigger, overhead gets cut down. So the actor model is not a solution for everything, but by sizing things in the right way and then using the actor model, you can find a sweet spot so that actually things work very, very nicely. So the idea maybe would be, if you ask an actor to do some work, think that it has to do about a millisecond worth of work. And if you do so, then you will probably keep up with the messages. In fact, you can send in the order of about 10 million messages in a system with a very good implementation of the actor model. Okay. Now, actors are more than this, right? It's not clear at all that you need a separate thread for every actor. And it's probably a bad idea to have a thread per actor. Why are threads bad? They require a different stack. And it's not clear at all that these actors will require a full stack. If you get away without a full stack, a stack, it's a very complex thing. I mean, you usually have to reserve at least 4 kilo for a stack because of the hardware and all kinds of complications. Managing the stack is very problematic. Switching threads is very problematic. The act of switching 2 threads cannot be done too fast. You cannot have million actors and actually have a thread-based implementation. There is no pure thread implementation in any operating system that can scale to millions, right? Thousands, yes. Tens of thousands, OK, but not millions, OK? So, but all of those are implementation issues as long as you have the actor model. Okay? So what are actors? Is lightweight objects, right? They have some behavior. That means I see these messages, I send these messages, and I do some kind of computation. They have local state. They never share the state with anybody. Whatever they have to say goes in the message, right? They have a mailbox. Now, this turns out to be extremely important because, for example, especially for the boss, if it's not fast enough for a few milliseconds to deal with the messages have to queue up. You definitely don't want whoever wanted to do something to be now stuck because the boss cannot take the message, especially if they have more work to do. And you can design the actor model so it's like this. So it's very important to actually have a mailbox. So that means there is no need for a so-called rendezvous that Ada language had. A rendezvous means 2 threads at the same time agree to talk and then they exchange some kind of a message. No, these are asynchronous messages. If you want to send me a message, that's kind of something queued in a mailbox and I'll look later at the mailbox. More like the email. Much faster, but like the email. Okay? Good. Right? So this is an example, for example, right? So this is a set of actors, right? You can have classes for these actors. This is one set of actors and send messages. Another message, another message. How you deliver the message, how you transport them, it's a different story. Now, the nice thing is once you have these actors running on a single machine, you can actually put them on multiple machines. As long as you can transport messages through some kind of a TCP/IP connection, you can have a truly distributed system with actors. And in fact, the framework I'm going to ask you to use, AKKA, right? Not only has local actors, but in a very natural way has remote actors. With very simple syntax, you say, hey, yeah, start another server on another machine, and hey, I can send messages now to actors that are remote actors by creating so-called proxies. Right? So you create essentially a local proxy that behaves like an actor, but in fact relays the message to another remote actor. So in a straightforward way, code you write to run on your 4-core desktop can be placed on a 100-machine cluster to run using the remote actors with almost no change to your code. Now, in what language is this possible, except these kind of languages like the Erlang or Scala, right? So a classic type of fault tolerance, as I mentioned, is supervisor, and there is a name for this, right? So a worker dies, hey, spawn off another worker. You just watch them, right? So you can have 1-for-1 restart strategy. One worker dies, I start another worker. Letting the code die, it's a much easier way to deal with the problem. And this is a very, very big issue. Is if you find an error in your code, so everybody says, hey, you write code that detects errors. Fine, you detect errors. Then what? Right? So you try to read the file and you cannot read the file. What do you do now? You're part of a large database system. The favorite way is you crash the whole program and say, I can't do this, right? It's not going to work. I mean, not in a telco system that has 99.99999 uptime, right? So I mentioned Akka. Actually, this is done commercially, but the code is available as open source. They self-support, and this is how they survive. It's part now of something called a type-safe stack. They actually have done much cooler stuff, right, which I'm using now. They design an entire web design platform. It's called the Play Framework. It's written in Scala and uses Akka actors. And you can design large website installations using actors. And that would be a nice thing to do because when you get an HTTP request, you can use these remote actors to ask different machines to do some work and then send the result back, all kinds of things like this. Okay? Now, it's implemented in Scala, but it has Java hookups. So it's a good implementation for Java actors as well. All right? And they have something else called software transactional memory, which I'm not going to go into. And here is some code for this. Okay? And this also shows another interesting example of this. Let me see if I can magnify this. Of this case classes. So I have something like this going in my code in C++, but it's a much, much heavier mechanism. So this case object increase essentially says there is a class called increase. I haven't specified more about it, but I could, right? But this is, so if you say case, that already has a default constructor generated and a default way to access any member that's inside. In this case, it has no member inside. By the way, classes themselves carry information. If I send you a message and the type of the message is increase, I already told you what I want. I want you to increase whatever, and this is happening with the counter. So I really need no content for that object. I just, the type of the class is the message itself in this case. So I'm going to have two classes, increase and get count. I'm implementing some sort of a counter actor. And this is the definition of the actor. I have class counter extends actor, which means has all the facilities in actor. In particular, it's going to can redefine this receive method, right? And this receive is going to be called every time a message is delivered to the actor. And that's what the Akka framework does. It's magic happening behind the scenes. Right? So what is this? Well, essentially you can define it to be a closure, and in particular immediately do one of those magic. So there is some kind of a magic match there, right? Because this is a receive is always written like this, and it's plugged in inside the match. Remember that code composition that we see with try? So receive, it's a closure that gets plugged into a match statement and puts these cases inside the match. So when a message is delivered, this closure gets to be executed, and then you have this powerful matching that says, if the type of the message is increase, then, oh, I just increment the counter. By the way, the counter is a private variable, so it's mutable of this class that got initialized at 0. If the message is get count, then I need to reply. There are nicer ways to reply, right, than this, but you could call the reply method. Okay? Reply, it's a built-in thing into the Akka framework that essentially says, send the message back to whoever sent me a message. So implicitly, you know who sent you a message. And we're going to get back to that in a second. Right? And that's it. That's my counter actor. Right? By the way, This counter actor now plays the role of a safe counter, right? As long as delivering messages is thread safe. So all you need to worry about in your actor framework is that delivering messages to an actor is thread safe. You don't need then to have shared variables that are protected by a mutex. You simply make an actor the guardian on one of these variables, and if you need to read the value, hey, send me a message with the value. Now, this is not going to be fantastic if you want to do many such small things. So you might want, for example, the actor to be responsible for a large hash and not for each entry in the hash a different actor, right? But it provides this interesting separation. As long as this guy keeps a variable counter private, nobody has access to it except if it sends a message and then gets a value. You're perfectly fine because you have thread safety on the message delivery. Okay? It doesn't matter how the actor is implemented. Okay? Okay, so how do you create these guys, right? These are the libraries, import, aka, actor. This is fancy stuff with libraries in Scala, which I'm sure you're going to enjoy when you read about it, right? You have things like actor references. Now, why would you need actor references? How else would you know where to send the message to, right? Now, if you create an actor, you implicitly have some sort of a reference to it, but it would be nice if actors can find out about other actors from other actors. And then you can just let the word go around. An interesting thing would be to ask a boss which actor could answer my question. We do this all the time when we try to accomplish things as humans, right? You go to a librarian and ask, or maybe to somebody in the department and say, who's the best number theorist, right? Say, that person. Good. I got an actor reference, right? Talking face-to-face with a person, in fact, it's a way of sending messages. I mean, your brains are not connected, really. It's just some sort of messages. Or maybe you send an email that's really a message, right? Same here, right? So references, this reference can actually be copied, which is very important. Then I can keep a reference myself, but if somebody asks about another actor, I can say, yeah, this is the reference. Now, here comes the fun part. Special operator to send a message to an actor. You say, counter, bang, increase. This is the operator to send a message. Behind the scenes, it just calls some kind of a send message. But this is nice syntax. Now, it's very important to understand what this does. Okay? So if you use just the bang operator, remember, counter, it's an actor, or a reference to an actor. Right? In this case, yes, we say counter, it's an actor reference, and any framework that has actors will have a way for you to find out what an actor is. Might be some global registry, or maybe you know from another actor what it is, or whatnot. Okay? So this sends a message, but this sends an asynchronous message. We're going to go through this synchronous versus asynchronous throughout the class because it's one of the central issues in distributed systems. Asynchronous means something like send and forget. To send a message asynchronously means you place the message in the mailbox of the other actor, but you're not waiting for that actor to read the message and do anything about it. Depending on the framework, the message might get delivered instantaneously or not, or never. Right? You don't care. The bank says, send it and forget about it. Now, this is really one of the best ways to get interesting stuff going, because nobody waits for anybody. I might check later, or I might get a message later, whether something happened or not. I should be concerned if the message gets lost, because that's problematic. But if I'm guaranteed that the messages don't get lost, I don't really care when that actor necessarily picks it up. For example, imagine that you have workers, and the workers compute these logarithm tables. You can actually do some very interesting thing, for example, if you want to take a vacation, right? You can basically say, hey, why not send work in advance to this guy? So what I'm going to say is, I know I'm not supposed to give them more than, let's say, 10 entries in the table, because they're going to be upset. We agreed on 10 entries in the table per message. Fine. But nobody prevents me from sending 100 messages, and they're going to queue very nicely. Now, since they have to do work for every message, they take the first message, they work on it. By the way, in Akka framework, you can't even tell how many messages you have in the queue. So to you, it looks like you just have one message. You have one message, you process it, and then you say, I'm done with the message. Immediately, the framework says, hey, you have another message. You even send back a result. You can still go on vacation because all the results queue up nicely in your mailbox, right? If I already gave work to everybody, and nobody is watching me to know I don't really do any work, I could be sneaky and go on vacation, right, as an actor. So I could go to sleep. But by the way, that's a big luxury, because then you say, there's no reason to keep this actor alive. Let's make him sleep and come back once a second. Because so what? It pile up in the mailbox. I don't need to work that fast on it. The other guys have work in advance. And you might say, oh yeah, that's a cute example, but it's useless in practice. I actually use it in my own database engine to keep the hard drives going at maximum speed. You queue up requests in advance for the hard drive so that immediately once they finished one request, they immediately make another request for the hard drive. So there is no gap in not keeping the hard drive busy all the time. So it's a very, very nice feature to be able to queue up requests for an actor. And you do it naturally. You just send them more stuff before they ask for it, right? And the results come and everybody's happy. That way, you can do this kind of double buffering techniques in which you overlap two operations at the same time in a natural way. You just send messages before they are needed because you know what's going to happen there, right? Good. So bang, asynchronous message. Don't wait for it. Done. Double bang. By the way, Scala has actors itself. And Akka, it's a different actor library. The Scala actors are a little bit different, and they have slightly different variations in the actors. I strongly suggest you use Akka because of the remote actors and because it really scales to large number of actors. So don't even bother with the normal actors. Use Akka actors, my advice. Okay. Last time I taught the class, I asked people to use either, and all of them inevitably ended up with Akka, right? Much, much better supported. Good. So double bang. Double bang means send the message, but then wait for a reply. The reply then, you can do some manipulation. In this case, cast it to an int. Okay? And then you put it in this value. So the behavior of this is you send the message, and you're blocked there until the reply comes back. Now, how do you think this is implemented? Well, the message is still asynchronous. The Akka framework only supports asynchronous messages. But what you do is you immediately do some kind of a receive after you've done the send, and you're waiting only for a specific message. That's a special facility in the Akka framework, right? And you block yourself exactly like you would block if you have no messages in your own queue until the answer comes back, right? So the double bang means send the message but expect a reply, okay? But it gets better than this. Yes?
Something that I missed here. What increase mean? What's the value of increase?
Okay. So increase what?
In asynchronous message.
Ah. So anybody, what's the value of increase? It's just the type itself. Has no value. It's just the type itself.
So if I want to send...
I mean, so implicitly means increase by 1. We could edit a value, increase by what number, and then it would take a constructor with what the number is. But in this case, it needs no value. So this is a strange situation in which you have a useful class that has no members.
Oh, then I send message first, then I increase the counter to...
No, but you see, you don't care what's inside the increase. You just care that you got an increase versus a get value, right? So this is an interesting situation in which the type of the message is the entire content of the message. There's nothing beyond the type of the message when the message is just increase. Now remember, you can send anything in a message, and you have somehow to encode the type of any specific message you send inside, right? So there is information shipped, but the information is only the type of the content, but not any content for the content, right? 2 more on this. I mean, look, if it works, it's great, because then types can serve as snippets of information themselves, right? Now, I don't even think this is possible, actually, in a language like C++. The compiler is not going to be particularly happy if you have no member. Well, maybe. I think the compiler might be very confused with these things. You at least need some virtual methods or something to get something going, right? Compiler is going to say, now what, right? But in Scala, it's perfectly fine. Okay? Good. So now, free bangs. Okay? So what could you possibly do? A bang asynchronously send message. Double bangs means send the message, wait for the reply. But here is the thing. Waiting for the reply means I have dead time for that actor. By the way, dead time is really bad because that means I'm not processing any other message until the reply comes back. So it would be nice if I have the ability to look at the reply, because sending a reply is a nice facility, right? Otherwise, I mean, you can always encode. I mean, let's forget about this. Let's say we have no wait for reply and none of this triple bang, whatever that means. How could you deal with that? Well, what you could do is basically, but then it becomes more cumbersome. In the message you send a reference to yourself and agree with the other actor to send you some message back. But then you have to register another message, and you have to remember that you sent the message somehow to be able to check later that you had the message. So you have to do your own management internally to remember that your intent was to wait for the reply of somebody somehow and check it later. These operators make your life easier. Yes?
I have a doubt about the asynchronous and synchronous. For example, it's an actor A and it's an actor B. Actor A is sending a message to actor B, and there's another actor C who's already sent an asynchronous message to B. C has sent it first and it's there in the queue. Now actor A sends a synchronous message to B, so it's after the synchronous message, but it's just waiting for it.
Right. So I think we are running completely over time. But, OK. So the order in which messages get queued is not guaranteed by the ACA framework. Whatever.
My question is like, C has sent an asynchronous message first to B, and then A sends a synchronous message to B. So which gets
Right.
executed
So
first?
we're going to talk about this extensively anyway because it's a core issue in distributed systems. How do you implement these things? Look, ACA has nothing but asynchronous messages. Everything else is built on top of it to simulate it. Because you only have asynchronous messages, whichever ended up first in the queue, in the message queue, it wins, and that's it. Right? The system makes no guarantees whatsoever about in what order it delivers synchronous or not so synchronous messages. This is a core decision in the implementation of ACA. We are going to talk about how you could do other things. And you can always simulate synchronous messages with certain delivery guarantees using a pure asynchronous message delivery mechanism. And this is what distributed systems are all about. I'm telling you now only what ACA does, not what could be done. Yes? Good. So the triple bang returns a future. A future is a nice object that allows you later to say, OK, so what's your value? So you block only when you ask what the value is, but not at the time you get the future. So you can decide to do a lot more work or take a delay and say, hey, I know it's going to take at least 10 milliseconds to get an answer. Why bother? Maybe I can do some other work in the meantime. 10 milliseconds are up. Let's check the future. So these futures are very, very interesting and important kind of mechanism in Scala in general, and they are used by the ACA framework. OK? Good. So have fun with Scala. Start Googling for resources for it and so on. I gave you the brief introduction to the actors. Seeing examples is the best way to learn. And after the first assignment, I guarantee you that you will know what actor model does, or not get a reasonable grade for it. All right? So now, since we didn't take any break, I think anyway the class is supposed to. When is the class supposed to end? So am I about?
10.
So we're done. We're toast. OK, good. So I'll see you next time, and I'm going to continue with what distributed systems are all about. But keep on coming back to these actors, right? All the time you're going to say, with the actors, how do you do this?